This is the Enolates chapter, slides 21 to 29. Okay, now that we have an idea about the enolate as a nucleophile, and we've done some 1-2 additions, we're now ready to take a look at what happens when we form these alpha-beta unsaturated carbonyls. So we're going to continue on our trek through enolate chemistry, but I'm adding one more sort of nugget of complexity. Notice that I have up here a definition of what alpha-beta unsaturated carbonyls are. And we now know what an alpha position is, and I did earlier define where the beta position is. It's 2 over from the carbonyl. Now what we're going to do is examine what these systems do when they're reacted with a nucleophile. So first what we need to do is understand that these systems are more stable than their non-conjugated counterparts, right? So which one is more stable? A ketone versus an alpha-beta unsaturated carbonyl. Well, it shouldn't be any surprise that the alpha-beta unsaturated carbonyl is more stable. Why? Because it's conjugated. It has 2 pi bonds that can resonate. And they are even more stable than their conjugated diene counterparts, right? Like just a regular diene that we saw in a Diels-Alder reaction. Why? Because of the inductive effect of the oxygen. So you've got the electron density can sit on, at some point, a more electronegative atom, right? So if you're trying to shift the electrons through resonance and you have an atom that is actually electronegative, as opposed to just all carbons in the regular diene case, this is going to add to its stability. All right, let's look at the effect of having a withdrawing group as part of the conjugated system. Well, if you're going to write resonance structures, I'll draw every resonance structure available to us. That is one resonance structure where I just moved the pi bond of the carbonyl up towards the oxygen. Notice we can't go in the other direction because the electrons are always going to be going with the dipole, and the dipole is pointing towards the oxygen. Oxygen is greedily pulling all the electron density towards it. Never, and I'm going to draw it, but then I'm going to erase it, never will the electrons go in the opposite direction because that would be away from the oxygen. Another resonance structure, again, moving in the direction of the dipole. Try to draw it a little bit better here. Places still the negative charge on the oxygen, but the positive charge at the carbon down below. So ultimately, the carbonyl carbon and the beta carbon, carbonyl carbon, and the beta carbon are the 2 areas of electrophilicity. Partially positive for nucleophilic attack. So do you see how this is making it a little bit more complex? If we don't have the alpha-beta conjugated system, then we only have the carbonyl to attack. But now, because of conjugation and because we have a dipole, by resonance we can see that there are actually 2 electrophile sites. This may complicate matters. All right, so another thing to pay attention to is the fact that this conjugation is highly stabilized. So whenever you're running or designing a reaction and you end up having molecules where there's a double bond, just shy of being conjugated, you have to be really careful under strongly basic or strongly acidic conditions. Here's why. We know that the alpha position is acidic enough to be deprotonated. And in this case, it's even more acidic because it's allylic to the double bond and alpha to the carbonyl. So this is going to increase its resonance big time. So let me just, actually, you know what? I'll draw it as the enolate. I'll push the electrons all the way up like we were doing to form an enolate, and we'll go from there. So there's the enolate, and we've got water. And so if you ended up quenching this with water and a little bit of acid in a workup, say you were doing some chemistry, when you work this up, the electrons are going to come back down. Oh my goodness. I don't know why it's being so, I am not shaky. It's just going to cascade and give you the alpha beta unsaturated carbonyl. So under basic conditions, this is called an isomerization. And the driving force for this isomerization is to get to the conjugated alpha beta unsaturated system. Likewise, you can do the same under acidic conditions. Under acidic conditions, the enol actually is existing. And if the enol exists, we've got HSO4 minus. That is going to act as our conjugate base for the alpha position. Forms the enol. And when you tautomerize everything, it's actually, under these conditions, going to stay as a conjugated system. So there you have it. You ended up again at the alpha beta unsaturated system. It isomerized. So it's just a word of caution that if you're ever trying to design a molecule with a double bond that isn't quite alpha beta unsaturated, but one step removed, it will find a way under strong acid or base conditions to get to the more conjugated, more stable position. Despite this added stability, it is not aromatic. Okay, we're not talking about the level of stability that we saw in the aromaticity chapter, where all of the reactions we saw with double bonds didn't work, right? The alkene chapter reactions were out of the door because the stability of the double bonds in an aromatic ring were so stable, and we had our own chapter dedicated to their chemistry. So like things like this, was no reaction, or this Br2 was no reaction. Okay, this is not the aromatic chapter. So I just wanted to highlight in this reaction that even though there is alpha beta unsaturated double bonds and they are stable, you can do hydrogenation on them. You can brominate them. You can still do an epoxide or dihydroxylation. You can still perform all the alkene chemistry even if it's an alpha beta unsaturated system. So that's just a word of note here. Okay, so what do we have to be aware of? Well, this is the last, oh my gosh, we finally got here, the last mechanism on our mechanism motif sheet. We've covered 1-2 additions in an exhaustive fashion. Now, as I showed you on that previous slide, there are 2 electrophile sites. So if I have an alpha beta unsaturated system and I introduce a nucleophile, let's just skip and say, I know you might say, well, how do I know if the nucleophile is going to go at this carbon or if it's going to go to the carbonyl? How am I going to know this? Beta carbon or carbonyl? What do I do? Well, let's handle that after. Right now, what I want to say is if we have a nucleophile that does attack at the beta position and not the carbonyl, what are we faced with mechanistically? Okay, so the nucleophile attacks the beta position. Notice the flow of electrons all the way up. We've added the nucleophile. We'll call this carbon 1. The nucleophile has been added to carbon 1, and now you can see that the electrons flowed all the way up to the oxygen. So 4 atoms were involved. This is a 1,4 addition, as opposed to a 1,2 addition where you attack the carbon and push the electrons up. There's only 2 atoms involved, a 1,2 addition. Here, we're involving a whole series through the flow of electrons from 1 to 4. After you've added the nucleophile, this new reaction, this is the only new part, mechanistically. Once you get to this middle intermediate, what do you see? What do you notice about it? You recognize what this species is? It's an enolate. From here, this enolate behaves exactly like we've been doing in this chapter. We can do a 1,2 addition with it, introduce a new carbonyl, and make the, again, it's the carbon right here. The enolate carbon would attack the carbonyl, and you'd end up with the product shown above. Perhaps you want to do a 1,2 addition with a better leaving group, right? You have a leaving group on here. So you use the enolate to attack in a 1,2 fashion, in, up, and do down, out this time. So the 1,2 addition I did in the beginning is just in, up. This one is in, up, down, out, because we have a good leaving group, the X. And then you end up with a 1,3 carbonyl. Or maybe you just want to do an SN2, right? You can take your enolate and do an SN2. And the carbonyl, the blue carbon, attacks R and kicks out the leaving group, and you've placed R at that alpha position. Or maybe you just want to work it up at this point. You're done. So you're going to add some acid. The enolate collapses, and the blue carbon just grabs a proton, and you're at the bottom here. So those are your options. But understand that this is only the new part, the beginning. Once the nucleophile attacks the beta position and you cascade the electrons all the way up, you are smack dab in the middle of old chemistry. Well, old given that we just learned it in this chapter, but before this slide, up till this point, the rest of it is repeated chemistry we just covered. The good news is that for the most part, the reactions that we covered that were indeed 1,2 additions, like the Grignard reaction, are still going to be 1,2 additions. And we will start seeing other types of nucleophiles, some new, some old, that are going to add 1,4. So when 2 pi systems are involved, you have a choice, okay? 1,4 or 1,2. So you have to start recognizing this alpha beta unsaturated system as almost its own functional group. Like, consider it one huge functional group. And you end up having regioselectivity issues, right? Do I attack 1,4 or 1,2 with a nucleophile? Right? This is a regioselective issue. Because if you consider it one massive functional group, you're not sure which part of the functional group, which region of the functional group your nucleophile is going to attack. So that's what I wanted to discuss next. I first want to do one full reaction with a very common 1,4 addition nucleophile. So let's just explain that I'm going to use this Gilman reagent. And an example of a Gilman reagent is dimethyl, that's the R, 2 R's, lithium cuprate. Okay, what does that look like? Well, dimethyl, the copper is negative, and the lithium is the counterion. So that's what this dialkyl or dimethyl cuprate looks like. What do you notice about the negative charge? What atom is it on? Well, it's on the copper. So what happens in this reaction is the copper is actually doing the attacking. That's different. The metal is attacking? I know. This is a little foray into organometallic chemistry for real. We still form our enolate. And the reason why I'm showing this one and showing you the copper is because I want you to see the distinct difference between this and a Grignard. It was the copper that ended up doing the attacking. Okay? Now, this is where in the next step, we have something called a reductive elimination. And what happens is one of the carbons and the carbon of the beta carbon join together and release the copper methyl. So what is going to happen? So I'm kind of telling you the real story. And the copper with the 1-methyl leaves as a neutral species. The lithium is hanging out up here with the oxygen. So the methyl copper just goes away. So that's the weird part. So this is, right? That's weird. Sometimes what I used to do is tell my students that just pretend one of the methyls is the nucleophile, but understanding that the copper is really the nucleophile, this will help you when you're starting to try and figure out when to go 1,4 and when to go 1,2. But if you just think about this reaction as, oh, I'm adding one of the methyls on and it's going to be at the 1,4 position, right? You should be fine because we get to this same position. We put the methyl group on and we end up with our enolate. Okay, and then we're going to do some electrophile and we don't know what to do from there. But at this point, moving forward, this is just an enolate reaction and we know how to do those. So I'm going to continue this reaction, that's why I have a question mark, on another slide. Okay, so let's talk about this. How do I know when the nucleophile goes 1,2, that would be the A, or whether it goes 1,4, that would be attacking like B. So we've separated these into hard and soft nucleophiles. And like solubility, hard nucleophiles prefer hard electrophiles and soft nucleophiles prefer soft electrophiles. How do I know what's what? Well, hard nucleophiles have a very tight, small electron shell, while soft nucleophiles have a much larger, squishier electron shell. So I'll represent that using the blue. They're both electropositive, but one is a bigger, fatter electron cloud, and the other one is smaller. So the tighter shell is the one closer to the oxygen. Maybe because the electron density is pulled up towards the oxygen a little bit better, tightening that shell. So the hard nucleophiles that will attack A are enolates, a deprotonated thioacetal, Grignards and alkylithiums, we saw those. We've been attacking 1,2 with those already. And also the alkyne, a deprotonated alkyne. These are all small, hard carbon nucleophiles. Notice that they're all carbon, right? Carbon attacks, carbon attacks, carbon attacks, carbon attacks, carbon attacks. Okay, Here's another trend for the soft ones. In the soft ones, we've got larger, squishier electron clouds. And so if any atom that you're attacking is not carbon, like a nitrogen or an oxygen, those are going to be softer and they're going to attack 1,4. So that's easy. So something other than a carbon typically attacks 1,4. Typically. Also, this is an enolate down here, but this is a much larger enolate. Think about the resonance of this guy. This resonance is over 5 atoms. The electron shell is much bigger and squishier, therefore. The electron cloud is much more delocalized, so it's considered squishy and soft. The only one that seems weird to me is the nitrile. Carbon triple bond nitrogen is actually a soft nucleophile, and that's the only one that's hard to interpret. The cuprates, on the other hand, although the carbon ultimately goes on, in the previous slide, I showed you that it really isn't the carbon that's minus. It's a big, huge metal, copper, with d orbitals and squishy shells, right? So big electron cloud of squishy orbitals. So it's really the copper that's attacking. So hopefully that will help you in understanding that, yeah, the copper does the attacking. It transfers one of the R groups on eventually, but it really is the copper that's doing the attacking. Thus, it falls under the soft nucleophile category. These are also called Michael donors. And so if you understand which nucleophiles are hard and which ones are soft, you'll be able to tell which ones do a 1,2 addition and which ones should do a 1,4. Now, I just want to point out these soft nucleophiles, okay? So let me just take the nitrile, for instance. If I had a ketone and I introduced a nitrile, it would do a 1,2 addition, okay? This is a question I get a lot, so I just want to make sure I clarify this. So I just showed you a 1,2 addition. I'm not saying that these molecules can't do a 1,2 addition. I'm just saying that when they are posed with a choice, they will prefer the 1,4 over the 1,2. But if 1,2 is the only choice because your starting material isn't conjugated, then it's going to do a 1,2 addition. The only exception to that may be the cuprates. If you wanted to do a 1,2 addition and add a methyl, you'd want to use a Grignard. But other than that, it's not that these other atoms wouldn't attack in a 1,2 if that was their only choice. It's just that when given the choice, regioselectivity of these prevails in one direction or the other, depending upon their soft or hardness. Okay, so the other thing that I mentioned was that oxygen and nitrogen nucleophiles, they fell under soft nucleophiles. So I just want you to be aware that those nucleophiles are soft, and I just want to reason why. So if I had introduced, I don't know, something like acid and water or NaOH, right? So let's say I had this carbonyl and the nucleophile I chose was NaOH minus. Understand that if I did a 1,2 addition, this is a hydrate, and hydrates are not stable. So when this collapses, it's just going to give me back my starting material. So we're not saying that the NaOH doesn't attack 1,2. It probably does, but it doesn't lead to anything very productive. As opposed to if the OH minus had attacked at the 1,4 position, now if the enolate collapses, it's not going to just kick out the OH minus, it's probably going to just protonate from the water that you formed. This actually gives us a 1,4 addition. So it actually can get someplace other than back to itself. So that's why we end up seeing these 1,4 additions with the softer nucleophiles like water, alcohols, and amines, because 1,2 additions actually don't take us very far very quickly. Okay, so I just wanted to do a bit of a review on, now that we've discussed what happens in a 1,4 addition, I want to focus a little bit more on the back end. What happens when you get to that enolate and you quench? So let's say that I started with, actually I'll write it up at the top. Let's say I have a soft nucleophile. So I'm going to do a 1,4 addition. I go in and up all the way. So what I've done is I've attacked the beta position. I have an enolate and I have a choice. So I'm going to write this 3 times and show you 3 different scenarios. Kind of already showed you each of these, but we're going to reiterate just to make sure. So you attack the 1,4, your nucleophile is now at the beta carbon, and you end with an enolate. You can quench it with a proton doing acid-base chemistry. The enolate, and again, just remember your enolate carbon is the one that's doing all the attaching. So it collapses down and protonates. Your new product is this ketone with the nucleophile at the beta position. Right, so you added a new bond at the beta position over here, the 1,4 addition. Maybe you wanted to do an SN2 and you added this primary chloride. Again, the enolate is what's doing the attacking. The enolate does an SN2. And in this case, the beta position has the nucleophile. That alpha position just added 3 carbons. 1, 2, 3. 1, 2, 3. Right? Because the alpha carbon is the one that attacked carbon 1. Lastly, you can quench with, I don't know, like a carbonyl, like in this case I have an aldehyde. This is a 1,2 addition. The enolate comes down, the carbon attacks 1, 2. And we have the nucleophile still attached to the beta position. We formed the carbonyl. It's basically us doing an aldol, right? From here, you have 2 choices, right? This is an aldol. And so you can do the reaction itself and just quench with a proton, giving you the alcohol. Or you could heat it up and, well, I'll just write it from here. You could heat it up and get the condensation product. You could heat up the product that you get, maybe add a little bit of base in there. As long as you have another alpha proton, something in there, maybe the strong nucleophile can act as the base, take off the extra proton and eliminate to give you the double bond that is now conjugated to the carbonyl you started with. So we're starting to mix all of these reactions together, and this can feel very daunting, but you gotta learn each one step at a time. That's why we covered enolates first, and then we started to add on towards the alpha beta unsaturated carbonyls, because it's really just more of the same. If you know what you can do with an enolate, you'll be able to handle these reactions no problem. Slide 29 is practice for you, identifying the type of nucleophile you have, hard or soft, and practicing your 1,4, 1,2 additions.